Hello everybody. So now we're going to go over Merkle trees. Merkle trees are data structures that allow you to prove that one piece of information is in a much larger set of information without necessarily having all the pieces of information. It creates a very efficient way to prove that a piece of data is in a much larger data set. So if you don't understand how that shakes out, don't worry, stick with me. You'll understand by the end of this lesson. So first I'm going to talk about lists, right? I'm going to talk about lists, and specifically a list of hashes. If you don't understand what a hash is, you should probably go check that out before continuing on with this lesson. So what we're going to do is we're going to take a bunch of hashes here, A, B, C, D, and E. So each one of these is going to be a hash. So it could be, denoted by something like this. Whoops. 0x A, B, C. And remember, each one of these is going to be a 64 character hexadecimal string that's usually denoted with 0x because that's just the common way of denoting a hexadecimal string. So you have 5 hashes here. And what we want to do is we only want to commit one of these to our blockchain. Right? Maybe it's Bitcoin, right? We only want to commit one of these to our blockchain because we don't want to bloat the blockchain state. We want to keep it as clean as possible. We don't want to commit all of these things, but we do want to be able to prove that our transaction was inside of the hash so that it's recorded in history for all time, right? So what we can do is we can take these hashes as a list and basically concatenate it all together and take the hash of that, right? So if we do this, and we take the hash, we're using SHA-256, right? It's a one-way function, takes a much bigger set of data, hashes it down into a 64-character hexadecimal string, and we get some string, right? F2, 3, whatever it is. So now we have a much smaller piece of information that represents all the transactions that we had before. And if we ever wanted to prove, say, that B, maybe our transaction where somebody sent us some money is in B, if we ever want to prove that B is inside of our data set, all we need to do is take A, C, D, and E, hash them together in the same way that we did here, and then show that it's equal to the 0xF23. And remember, I'm saying that the 0xF23, this is what gets committed, right? So that's what's getting committed to the blockchain. So when we take these pieces of information, we're going to compare it to that history. And if we can prove that B concatenated together with these other transactions are going to create that hash, then we can prove that we are in that history, right? So that's the idea, is we're saving some space by only committing one hash. But one thing here is when you are proving that B is inside of this hash, you need to know about A, C, D, and E, which if the list gets bigger and bigger, it's going to be more and more information you need to keep track of in order to be able to commit up to that hash. So maybe we could do something that will save us a little bit of information that we need to prove in order to come up with this root hash here. And that's where Merkle trees come in. So Merkle trees are an awesome invention. Merkle trees. Merkle tree is going to be similar to a list in that we're going to have our leaf nodes. That's what I'll call them because it's a tree, right? That's pretty standard. So down at the bottom, so leaf nodes, we have A, B, C, and D. And what we're going to do, instead of just hashing them all together, is I'm going to hash each one individually together, kind of like a tree, right? So A, B, and C, and D, we're going to toss into our one-way function. So we're going to have AB, and we're going to have CD, and then we're going to toss those into a one-way function again, so that we have A, B, C, D. Okay, cool. So now what if we wanted to prove that B is inside A, B, C, D, just like we were doing before with a list? What would we need to know? We would need to know B, right? That's our transaction. We're keeping track of it. We would need to know A because we hashed it together to get AB. And we would need to know CD. Now, if you're looking, The two pieces of information we don't need to know are down here, C and D. We don't need to know C and D because if we just know C, D, we can hash it together with our product of A, B and come up with A, B, C, D. So we're kind of excluding some leaf nodes that we don't need to know about. Now this might not look like a lot of savings, right? Because if we just did it with the list, we would only need to know about 4 pieces of information down here, right? And we would hash them together all together, get the A, B, C, D. So it doesn't look like much savings. But where you do start to see some savings is when the list gets bigger and bigger and bigger. So let's look at a bigger list. So if we have our root hash here at the top, what we're going to want to do is we're going to want to be able to create a much bigger tree here. So I'm going to color in nodes that we're not going to necessarily be part of our branch with red. And then I'm going to color in nodes that are part of our branch with green. Okay, so at this top layer, we only have 1 node. This next layer, we have 2. If I keep going down, you might start to see a pattern. If I keep going down on this one, what do we have? Dun, dun, dun. We have 4. Don't worry, I won't keep going down all the way. I'm going to just shorten this a little bit. So maybe we have 1 here, maybe we have another one here, maybe we have 1 here, right? And so if I toss in a few green nodes, all right, cool. I'll do 1 more. Okay, so right here, we're going to have 16, oh, sorry, I skipped ahead. So 1, 2, 4, 8, 16, 32, 64, and 128. So down at the bottom here, on either side of this node, altogether we're going to have 128 leaves. So it's going to be a very long list, right? So if we were going to do it the way that we initially did, where we were going to hash everything together like a list, we would need to keep track of our transaction plus 127 other transactions, right? That's a lot of information to hash together. But if we're doing it the Merkle tree way, the efficient way, we only need to know 1 piece of information for every green node that's here, right? So we would need to know the sibling of this one here. We need to know the sibling of this, 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 all the way up to the root. So how many pieces of information is that? 1, 2, 3, 4, 5, 6, 7. 7 pieces of information for a 128 leaf tree. What that comes out to be is you're going to need to know this amount of information, where n here is the number of leaves in this tree. So if I plugged in 128 into this equation here, the logarithm 2 of n, 128 is going to give us 7. If I did 256, the logarithm is going to be 8. And so you can see that every time we multiply by 2, we go 1 layer deeper. We're only adding 1 other piece of information that we need to know about in order to prove that our transaction is in this root. And that's the beauty of Merkle trees right there. It's efficiency. It's allowing us to only keep track of a few pieces of information to be able to prove our transaction is in a root. And so we're always going to be part of that history, even though that history might only be 164 character string, 64 hexadecimal character string, representing a much larger set of transactions. Cool. So now we're going to dive into some coding exercises. We're going to build our own Merkle tree here. I want you guys to be able to first come up with a way of combining 2 nodes together to come up with a Merkle hash, and then we're going to move on to the next layer and the next layer until we can actually create a Merkle tree from something as large as 8 layers deep.